Hello, BC Calculus students. This is Mr. Johnson, and this is section 3.5, which is on implicit differentiation. So we just got done with looking at parametrics where we had parameters based on, or variables based on x, y, and then t. So x and y were based on t. And we looked at how the chain rule worked with finding the derivatives of those particular functions. And so what we're going to talk about now is implicit differentiation, where we may have x's and y's that are mixed up on one side of the equation. We have to handle the derivative of that. Ultimately, we'll get into then related rates when it comes to finding out the rate of change of a function based on time, written implicitly. So first off, what is the difference between explicit and implicit? Well, an explicit equation is written sort of plainly, where y is a function of x, and when you look at the function, you can see that the y's and the x's are separated. You'll have something that might be linear, y equals 2x plus 1, parabolic, something that y equals x squared plus 2x minus 4, and you're looking for functions that are kind of plainly stated, and they are separated in terms of their input versus output values. Implicit is going to be not as directly stated, and so you may have something, one of the most common ones is a circle, for instance, where you have some sort of graph that is not a function because it doesn't pass the vertical line test, and so therefore you have variables that are both the input and output are on the same side of the equal sign. You may have something more complex where they're even mixed up within a trig function, and that's what we're going to deal with in this lesson, is how to calculate the derivative of graphs like this, because we still are interested in what the rate of change is, for instance, for maybe a vertical tangent line or something along those lines. So in example 1, let's take a look at a circle with a radius of 3. This is implicitly defined because the x's and y's are on the same side. You're unable to solve for y, which is one of the signs that this type of equation is going to be represented in such a way that we have to do an implicit derivative to find a rate of change. So if you were to try to solve for y, for instance, you would have both a positive or negative square root 9 minus x squared, and that would be representative of the top half of the circle and then the bottom half of the circle, which again just helps to support the fact that it's not a function. So if we're going to find the derivative, what we're going to do is we're going to take the derivative with respect to x of x squared plus y squared is equal to 9. And the derivatives with respect to x, which means that if we have anything related to x, we're treating it really the same that we have all along. So for instance, the derivative of x squared is simply just 2x. The derivative of y squared, we're going to treat that almost like a chain rule situation where we have something squared, which means we do the power rule first. So that's 2 times that something to the first power, but then the something that's in the inside, which in this case is y, is implicit because we're taking the derivative with respect to x. So the derivative of y with respect to x is dy dx. So the reason for all of that is that we just performed the chain rule on y because it wasn't the variable of differentiation. And then the derivative of 9 is 0. As a side note, just to keep in mind what's going on here. So remember, again, if we're taking, for instance, the derivative of x squared, which we just took, we get 2x. If we take the derivative with respect to x of y squared, we got 2y. However, we needed to multiply by dy dx because this was implicit due to the fact that the derivative of, or the variable of differentiation was x, while the value there is y. Let's say that we switch tables and we say, well, we're going to differentiate with respect to y, x squared. Well, we're going to get 2x, but this time we're going to get dx dy because, again, y doesn't match that variable of differentiation. Or let's say we took the derivative with respect to y of y squared. Well, now we're just going to simply get 2y. If we were to change gears and look at maybe related rates and take the derivative with respect to t, well, now we have 2x multiplied by the derivative of x with respect to t. So hopefully you can start to see this pattern of implicit derivatives. Again, this is very important for what we're studying here. Okay, let's go back to this example. So we have our generic or our first step for this formula, the generic formula for the implicit derivative. And we're going to now just simply balance. So we are ultimately solving for dy dx by first moving over 2x, and then we're going to divide by 2y, and we get negative x over y. That's going to be representative of our slope. And I want to see if I can help you kind of intuitively understand why this makes sense. So if we have a circle with a radius of 3, centered at the origin, okay, if you were to look at that graph, where would you envision, or where can you see a vertical tangent line? Actually, let's back up. Let's start with the horizontal tangent line. We can see that there are horizontal tangent lines here where there's a slope of 0, as well as here where there's a slope of 0. So the question is, what is the x value at those points? Well, the x value at those points where the slope is 0 is going to be 0. In this case, y is negative 3, and here we have 0 and y is positive 3. Now, if you look at our slope, and you were to plug in 0 for x and 3 for y, or 0 for x and negative 3 for y, you can see that the slope is 0. So the slope kind of backs up the idea that those two are horizontal tangent lines. Now if you were to look at vertical tangent lines, we can see that there's actually 2 of them. And these occur here when x is 3 and y is 0, and over here when x is negative 3 and y is 0. And if you look at your slope, now you are taking into account that the denominator is 0, which gives us this idea of an undefined value, and now we can see graphically what's happening to the slope. So this slope is undefined. The reason is that the particular graph has a vertical tangent line. And again, we could find tangent lines all over this circle, but the idea of this slope is that now that we're doing this implicitly, and we're getting a slope that's made up of x's and y's quite often, the question may be, when is there a vertical tangent line, which we really don't ask when an equation is written explicitly, because our slope is going to be in terms of x only. But now that we have these slopes that are more complex, where we have x's and y's, now we might be asked questions that are a little bit different, like when is the slope undefined, or when is there a vertical tangent line? Okay, let's go and try example 2. And again, all this stuff is review from AB, so if you want to pause and try this on your own and then check, you certainly can. We're going to find y prime. Now I'm going to write y prime as dy dx. I think this notation just is easier to kind of manage. I know y prime is easier to write down, but with so many x's and y's and all this stuff with implicit equations, I think that it's maybe easier to notate it as dy dx. Okay, so we're going to take the derivative with respect to x of x cubed plus sine y equaled xy. And we have our first derivative as 3x squared. And then we have our implicit derivative, so we have cosine of y multiplied by dy dx. And on the right side, we have a product rule. So we're going to take the derivative of x, which is 1, multiplied by y, plus x times the derivative of y, which is dy dx. Okay, our goal here then is to get all of the dy dx's to the same side of the equation, and all of their terms to the other side of the equation. So I'm moving the x dy dx over to the left by subtraction, and then we'll move the 3x squared over to the right because it does not have a dy dx in it. Then we will factor out the dy dx so we can ultimately solve for it. So we have cosine y minus x, and we simply finish by dividing by cosine y minus x, and we get our slope. And that's all there is to that problem. Okay, let's go on to example 3. All right, so example 3, same kind of thing here. Again, this section is just the main topic is implicit differentiation. So a similar problem. Again, if you want to pause, try it, and then come back and check, you certainly can. It says, what is the slope of the line tangent to the particular curve at the point 2, 0? So we're going to do the same thing here. We're taking the derivative with respect to x of y plus 2 equal to x squared divided by 2 minus 2 sine y. So our first derivative is of y, so we get dy dx. Derivative of 2 is 0. We have our power rule, so we end up getting x there, minus 2 times cosine y, and then we have times dy dx. And then similar to the last problem, we're going to try to group these dy dx's together. So we have dy dx on the left, plus 2 cosine y dy dx. And we'll go ahead and leave our x over on the right side. Then what we'll do is factor out the dy dx so we can solve for it. And then finish the problem by dividing. All right, now what we want to do is calculate the derivative at this particular point. So we have the point 2, 0. So we plug in 2 for x and 0 for y. And that gives us 2 divided by 1 plus cosine of 0 is 1. So we have a slope, of 2/3. All right, let's try our last example. So we have a particular implicit equation and we want to find the slope. So again, we're going to take the slope with respect to x of the natural log of 2x plus y equal to x plus 1. All right, the derivative of the natural logarithm is going to be 1 divided by 2x plus y. Now remember, we have to use the chain rule to multiply by the inside of the logarithm, which means that derivative of the inside of the logarithm. So we have derivative of 2x is 2, and the derivative of y is dy dx. And then over on the right, we just have 1. Okay, so there's a few ways you could solve this, but what I would recommend is to multiply both sides by 2x plus y. And if you do that, you're going to have 2 plus dy dx on the left, and 2x plus y times 1 is just 2x plus y. And what that does is it allows us to access dy dx pretty quickly. So we just subtract 2 to finish the problem, and then we just go up to find our answer, which is option B. Okay, so that is it for section 3.5 and implicit differentiation. Thank you.